All right, welcome everyone to our MIDRC seminar of the month of May 2024. Today we have not one, but two excellent speakers who will tell you all about the MIDRC Diversity Calculator. Our first speaker will be Heather Whitney. She's a research assistant professor of radiology at the University of Chicago. And within MIDRC, she's a member of the Bias and Diversity Working Group, the Collaborative Research Project 11, and Technology Development Project 3D, where she monitors diversity and representativeness of MIDRC data and fosters interoperability with the N3C enclave. Our second speaker will be Rob Tomek, and he's a member of the Geiger Lab at the University of Chicago, an experienced tech entrepreneur with a history of applying machine learning to the medical device industry. His research focuses on information technology, machine learning, medical devices, oncology, image analysis, and image processing. So basically anything related to medical image analysis. So how this is going to work, this seminar, first Heather will have a presentation followed by Rob, and his presentation will also include a live demonstration of the diversity calculator. And at the very end, there will be, both speakers will be available to answer questions. So during the seminar, feel free to put questions in the Q&A box, and then they'll be answered at the very end. All right, so Heather, please kick it off.
Hello, everyone. We'll get our slides started here. Thanks so much for joining us today. We're really excited to share with you a next step in MIDRC's work on bias and diversity. So today, Rob and I will be talking about the MIDRC Diversity Calculator, which is now ready for many of you to use as you wish. So we'll go to the next slide. So in this talk today, we'll cover MIDRC very briefly, just to get everybody on the same page. We'll talk about the activities of the Bias and Diversity Working Group within MIDRC, talk about existing MIDRC measures of representativeness, review just a few things that we've covered in the past, and then Rob will demo the diversity calculator. Next slide. Thank you. So just an overview of MIDRC. So as most of you know, the MIDRC Medical Imaging and Data Resource Center was initiated to respond to the COVID-19 pandemic, and now importantly, it's pivoting to include oncology and other diseases. But our foundational goals remain the same. It's a curated image and data commons, and importantly, a means by which researchers can address topics no single image archive could yield independently. And also importantly, it's a partnership between the organizations shown here. And there's two scientific components of MIDRC, an open discovery data commons. You can go to data.midrc.org even after this talk and start downloading data. And then also very importantly, machine intelligence computational capabilities. As a team, we develop clinically relevant algorithm and software tools to again facilitate translation of AI algorithms into clinical work. Next slide. And to facilitate translation, we have a few additional important activities going on. As you can see here, there's a pipeline of data that comes into MIDRC. We've ingested over 300,000 imaging studies. That data is undergoing MIDRC data quality and harmonization before it's released. And at this point, we have over 170,000 imaging studies that have been released to the public. And all of those images have undergone de-identification, quality control, et cetera. 80% of that data goes to the public commons, and then 20% goes to the sequester commons, which is important because it facilitates real-world testing of algorithm performance. And as you can see, lots of publications and presentations, lots of good things happening. And now as we introduce our work in representativeness, this was motivated because as you know, the field has seen lots of gaps in AI ML development, particularly a lack of diverse and representative data. So kind of a broad overview of some things that have happened in the field over the past few years. We've noticed that there's a limited geographic distribution of data to train AI algorithms and limitations on available group and subgroup data levels. And all of these have impacted the representativeness of AI algorithms. Next slide. So we see this need for large representative data sets. You can go to the next slide. Thank you. And if we kind of review specifically the pandemic and what happened with COVID imaging, a lot of things popped out. We've seen some news reports about why didn't AI tools help in COVID as much as was hoped. And in reflection, part of that was poor quality of COVID imaging data, lack of collaboration and communication between AI ML experts and biomedical experts, and bias and diversity. And that's why we have this bias and diversity working group at MIDRC, because we want to combat some of the issues seen previously in the pandemic. And one of these aspects was a lot of data was collected for just specific populations, which limited its generalizability. And another way of saying that is lack of diversity was seen in the data. So this motivates all of the work that the bias and diversity working group does within MIDRC. Next slide. So here's an overview of our working group. So the Bias and Diversity Working Group is comprised of a range of individuals from different representations of the different organizations that are contributing to MIDRC. Throughout our talk today, we're going to have several QR codes, so you can hold up your phone and grab those links, or you can come back to the seminar later on when it's posted to YouTube and go to any of them. But we have from this group a number of resources that are all available at midrc.org, coming from all this investment that we're making in solving the problems that were shown in the previous slide. Okay, next slide. And just to review the overall mission for the Bias and Diversity Working Group, our aims are to identify and mitigate bias in data collection, curation, and analysis by developing trustworthy and ethical machine learning algorithms to account for and reduce bias, to create and publicly share representative data sets, enable the study of sources of bias and their impacts on machine learning, develop methods to mitigate algorithmic bias, and sequester data as a tool for assessing algorithmic claims. So we can go to the next slide. So one brief tool I'll mention before I go on to the diversity calculator work is, you may have seen presentations on this before, but if not, we want to make sure you're aware of it. The Bias and Diversity Working Group has done a tremendous amount of work to create the bias awareness tool. And you see here kind of the different aspects of AI pipeline development that we studied and thought about what areas of bias might be present along the pipeline. They overlap, so a lot of analysis was done towards that. And you can go to this QR code or just midrc.org and check out the bias awareness tool even today. So that's one tool that was available. And then now I'm going to talk about on the next slide, our assessment of the diversity of the data. So in MIDRC, we're really excited to have data contributors from several different organizations, different sites. And you can see here our latest update. So maybe you've seen a seminar in the past, maybe about a year ago, I think we had a seminar on the representativeness of the data. So here we are a year later, and we have further updates to make about the data. So at this point, about 14 contributing sites have contributed data to MIDRC. And if you think about those numbers we showed on a previous slide about the different imaging studies that are available, if we tally that in terms of unique patients, we're looking at about 70,000 unique patients represented in the MIDRC Open Data Commons. And as always, we like to remind you that we're very much wanting to hear from anybody who wants to donate data. So you can go to midrc.org and maybe get your institution on our list of contributors. Next slide. So now what we're going to do is start to break down this data by different groups, because as you remember from the previous slide, it's really important to kind of tally your data and make sure you know where it's coming from and who it represents. And so, as I mentioned, we're about 70,000 unique patients. And here's the breakdown of our patients by attributes for which we kind of balance between the open and the sequestered data sets. Remember, this is the open data that I'm showing right here. And as you can see, we have different breakdowns of different categories: age and index, sex, race, ethnicity, race and ethnicity, and the COVID-19 positive, yes or no. And so our goal is to kind of walk towards a more quantitative understanding of these groups of patients with respect to different populations. We can go to the next slide. So MIDRC monitors the representativeness of the Open Data Commons in the categories I just mentioned. And right now we are working with two comparison groups. So first of all, we compare MIDRC, all the patients in the Open Data Commons, to the United States 2020 census. This is because all of our patients in this particular comparison group are from the US. And then for our COVID-19 positive patients, we compare all the unique patients in MIDRC from that category to the CDC COVID positive case counts. And these are the monthly cumulative case counts derived from data from the CDC, which the CDC reported out up until about May 2023. Go ahead. And so we monitor this both qualitatively and quantitatively. Qualitatively, we watch longitudinal area graphs. You can see here an update of our data. This is all unique COVID-19 positive patients. tallied by age ranges on the left. And then we do this quantitatively through the Jensen-Shannon distance. And I'll pause and emphasize that this has been kind of an area of focus of the Bias and Diversity Working Group. We wanted to kind of identify from the literature and from other statistical measures, what's a good metric that we can use to keep an eye on representativeness of the MIDRC data. So it's a nice metric, the JSD is, because a JSD of 0 says that there's complete similarity between two comparison groups. And then if it's a 1, that means there's no similarity. So we're looking at a range between 0 and 1, and that's a nice metric to kind of be able to represent representativeness very quickly and easily. Next slide. So just as an update, as an example of one of the characteristics, the attributes that we track for our patients, this is a figure of the JSD over time for comparing MIDRC, all the patients, all the unique patients in MIDRC to the census, and then all the unique COVID-19 positive patients to the CDC case counts. And remember, lower means more representative. It means less different. So as you can see over time, actually the comparison of our groups in terms of age index has stayed pretty steady over time, and also between these two comparisons, pretty similar. Next slide. So from this, we have been working on creating a diversity calculator as a general tool for AI investigators. So I want to emphasize this kind of one of two ways. One is we have our internal procedures for measuring representativeness. And in fact, we're kind of formalizing what that might look like as a service for anyone who wants to come to MIDRC and have us evaluate representativeness. And then on the other hand, we've been developing this in terms of an open source resource that anybody can use. And so Rob has come in and has done an amazing job creating a formalized tool that anyone can download and start using, either to measure, look at the representativeness of the MIDRC data, or to upload their own data for the purposes of evaluating its representativeness. So what you're seeing here is a QR code to the GitHub where you can actually go and download this. This QR code will also show up at the end of our talk. And then Rob is now going to discuss the mechanics of the tool and do a demonstration of how it works.
Okay, Rob, you're on.
Okay, sorry, my toolbar disappeared and I couldn't get it back. All right. So yeah, so thanks, Heather. I've created an interactive tool that's usable by the research community now, and it provides some real-time comparison via this Jensen-Shannon distance of our MIDRC data that we've collected for chest x-rays to the US Census and to the DDC. Our overall goal of this software is to provide a real-time comparison by this Jensen-Shannon distance to any user-selected data set, so that our goals are the user can select a data set, they can select their data characteristics on which to compare a data set, and then eventually select their output format. So I'm going to run through an overview of this diversity calculator, and this is a quick screenshot. There's a lot going on, and I'll be explaining it in a little bit. But I want to point out this is publicly available right now on the MIDRC GitHub page. So if you go just to the MIDRC page, we're not popular yet, but we are a new repository. So we're right here right on the MIDRC page in GitHub. So we can, if you check out the master branch from Git, there's some pre-formatted MIDRC data, CDC data, and census data. That's stored in Excel files that we use, and that's all currently available in the repository as well. So launching the diversity calculator, so it's Python based right now, and you can do it in terminal or in an IDE. There's some instructions in README. You can install requirements through pip, and I'm going to walk through the software right now. So slideshow. All right. So if we go to the GitHub page, so here's the MIDRC diversity calculator, and we can see the code. So we want to check out the master branch. There's lots of explanations on GitHub how to check out the code. There's some instructions as well. So there's a README file. So there's a lot here to get you started. But I'm gonna, start from the beginning and get things going to show you how to do this from the beginning. So I personally use an IDE to manage some of this. So I'm creating a new virtual environment and installing requirements. So I use PyCharm, and that does a lot of this for me. But right now, I'm creating a new Python 3.11 virtual environment. So it's usually best practice to create a new environment for each project you're working on. So, all right. So now that I've got my virtual environment, I can move into it and then install my requirements. So as I mentioned, there's a README file to kind of guide you through this. But we set up an environment, we install our requirements, and then at this point, the application is ready to launch. But I mentioned that we do have some Excel files already pre-created. So if you launch the applications, there won't be any files loaded, but there is a config file to automatically preload some files into the application so that when you launch it, you can use it right away. So there is a config file called, it's JSD config. So there's a JSD config example. So I'm going to copy it. There's already one that exists, but I'll copy it over the JSD config example to JSD config. And then at this point, we can launch the application directly. So launched on my other monitor. Here it is. So here's our diversity calculator that I mentioned before. And this is the default view if you use our example config file. So I mentioned there's files. So right now we have a MIDRC Excel file. So this is all of the chest x-rays that we've collected so far at MIDRC. I've loaded the CDC Excel file. So this is CD COVID positive counts over time and the demographic distribution of the CDC COVID positive counts. The census Excel file. So this is the entire US general population demographic distributions. And then the MIDRC COVID positive is similar to the MIDRC Excel file, except specifically only for COVID positive cases. So chest x-rays where there's a COVID positive test versus all chest x-rays. So Heather went over, the comparisons that we make with these earlier. So there's different attributes that we can look at. And so right now we're looking at age at index, and it's calculating all the Jensen-Shannon distances over time on the fly. So, and here it's displaying plot over time of this Jensen-Shannon distance, as she mentioned before. So for age at index, so we can look at the different attributes, and it's calculating them all on the fly. I'm gonna hide chart animations for this talk. So here we're looking at the MIDRC for CDC. So every time either the CDC reported COVID positive case counts, so demographics of the COVID positive case counts, or MIDRC collected additional data, there's another time point here, and we're seeing the Jensen-Shannon distance over time. So as a reminder, this is a distance measure. So a value close to 0 means that the two demographic distributions are very similar, and a value close to 1 means they're very dissimilar. So we're currently measuring representativeness of age at index between the MIDRC and the CDC Excel files. So we have all these different attributes, but we can also directly see a spider chart over here of the different attributes to see what's most representative, more representative and less representative. And sex is closer to 0, has a value closer to 0. So that means it's should be look more representative of the CDC file, and that kind of makes sense since it's close to 50-50 distribution for male and female compared to the other attributes. So that is our spider chart. Here we have pie charts too. So for each one of these attributes, right now we're looking at the MIDRC Excel file. So for each one of these attributes, there's a pie chart showing the distribution of the different age groups, sex, race, ethnicity. So every attribute that's in this menu, it's quickly showing our pie chart. So if we go back here, this is, I'll bring my back up. It's an example. So this would be like the pie charts over time, for example, this area chart. So we're looking at the age distribution over time. And this is correlated to whichever attribute we're currently looking at. So we're looking at age index. We don't have to view just the MIDRC file. We can view the CDC Excel file too and see what the distributions look like for both the area chart and the pie charts. And we can actually look at both at the same time as well. So here we have the pie charts. So we can see the MIDRC Excel file and the CDC Excel file and make comparisons directly between the two distributions to assess representativeness with the pie charts. And we can also look at here, we can see the area chart over time of the different age categories. So there's one thing about the CDC data is we notice there's a lot of not reported, especially early on for age. And then over time, as there were more reports by the CDC, it started filling in. There was a smaller percentage of not reported cases. So we can quickly compare multiple files against each other directly right there in these area charts. So this is nice for, I guess, just comparing these two. But I mentioned we had 4 files open. So we can actually compare as many files as we want. So I'll go up to 4 files. So now there's 6 different category or comparisons that we can make. So MIDRC versus CDC, MIDRC versus census. So each one of these files against each other. And a couple of things to note here is, so we have the CDC COVID positive versus the census. We can see early on there is a large, like very dissimilar age distribution between the CV COVID positive reports and the US Census. And then over time, it became more similar. So the distribution of COVID positive cases versus the reported by the CDC versus the census became more similar. And then this yellowish orange line is the MIDRC versus MIDRC COVID positive. So comparing all of the chest x-rays in the database versus the COVID positive x-rays, and we can see that the age distribution is actually very similar between the cases that had a COVID positive test versus not COVID positive. So once again, we can look at this for all of the different attributes. And I think one thing to note here too is like all this MIDRC is based on radiology data, but the CDC versus census is actually just, COVID positive testing versus the US Census general population. So this doesn't necessarily have to be radiological data. We're just comparing how does the CDC COVID positive testing compare to the US population as a whole. So I'll pull this data table back up. Another thing to note is, so we have all of this data here, and that's calculated on the fly. If you want to use another tool, we can copy and paste this. So for example, we can go into Excel and just paste our Jensen-Shannon distance data right away. So we have all the dates and the values from this table, and we can directly get it into Excel if you want to do further research or generate different plots if you're for just using the calculation. And you can use this data. Researchers can use this data further any way they want. So I mentioned, our input is Excel files, and how do we load this? And I'll just give you a quick example of a couple of our input files. So here we have our MIDRC data. So we have, the different tabs are each one of our attributes. So age, index, sex, race, ethnicity. And then we have each category is here a column heading. So what the software is doing is it's automatically parsing the columns and it's seeing which columns exist in all of the data files that are currently there. So we actually have an extra column here that isn't in the other one, but it's not being picked up because it's not in both. So we're not fixed to just these 5 attributes. It's whatever demographic distribution you're looking at, whatever attributes you're interested in, and you have biomedical data for, we can assess that using this tool. So we just need tabs that are similar, and then it assesses categories, and it's looking for categories where this name is identical to the name for the other file. And I think one way to show this is if I go back to just comparing 2 files, if I look at MIDRC versus MIDRC COVID positive. So I mentioned that there was like a COVID-19 positive attribute, and so there's actually, so we have all yes COVID-19 positive in the COVID-19 positive Excel file, and then percentage yes and no in the regular MIDRC Excel file for all of the chest x-rays. So it's actually pulling this up. There's actually a high distance because they're all positive in the COVID positive Excel file and not. So it's pulling everything on the fly here based on whatever our input data is. So it's fully customizable there. And one thing to note is we're expecting a date column too, so we're dates over time. So if you have like a static data, or if you just have one time point, so the U.S. Census has just the single time point, and we have data here for that. So there is in our example config file, it shows how to load static data as well. So there is already an example there. If you just have one time point, how to compare it. And then it'll pull in the dates here and see how this comparison changes over time compared to the static time point of the U.S. Census data. So big emphasis, so this is useful for any biomedical data. There's radiological data immediately available. If you pull this, that's shared for the MIDRC data for comparing against the CDC and census, or you could even, open. So there is a file open as well. So you don't have to use the config file to open an Excel file. So you can open up your own file and then directly right away, either compare it to the MIDRC data or compare it to the CDC or census. So immediately right away, you can start, say you're interested in some biomedical data versus the census population, you can see the demographic distribution right away. I guess in conclusion, so this is all open source, and like I said, I use PyCharm, so you can view and look through it. All the classes and methods have documentation right now, so hopefully a researcher can come in and they can view this and edit it and make changes or enhancements if they want to. There's also a back end as well. So if you just want to use the back end and load the data, there's examples there also on here if we look at the GitHub, there's also a Jupyter Notebook to show how to just use a pandas data frame and generate our, over time, our Jensen Shannon distributions and generate a plot too. So there's some examples there of how just to use the backend. So we have, there on the GitHub, there's instructions, there's clear documentation of these functions. So hopefully people can get in and, we'll see how other researchers might want to use this and edit it themselves, and any enhancements and contributions to this would be greatly welcome. So, so I'll go back and finish up. So, so we're assessing MIDRC representativeness. This is mostly bullet points of stuff I wanted to make sure I covered, and I did cover all that. It's Excel files with full customization and not restricted to radiology. This is fully open source, so you can get the code. It's documented, should be customizable. Like I mentioned, there's that sample Jupyter notebook. In summary, we can access this diversity calculator straight from the MIDRC GitHub page. And here's the link. There's what the MIDRC GitHub page looks like. And you can scan this QR code. I'll leave this up for just a couple more seconds. But yeah, if you just github.com/midrc, and like I mentioned earlier, we're a new repository, so it should be findable just by using github.com/midrc. And so we'd like to acknowledge Bias and Diversity Working Group, Gen 3, MIDRC Central at University of Chicago, and definitely Emily Townley for helping set all of this up. All right. And Heather, anything else to say, add?
No, that's great. Looking forward to the questions. Thanks, Rob.
Okay. Yes. So thank you to both our speakers. There are actually quite a few questions. So let's hope we can get through all of them. So the first is actually kind of a two-part question, and it's for Rob. So it says, and some of these have been answered in part already during the talk, but it doesn't hurt to reiterate maybe some things that people may want to have emphasized. So the question is, can we upload an Excel consisting of data from a public database which we curated to have the demographic info and use this tool for that file? And then part two of that question is, so as I understand this tool, it compares any type of attributes other than the ones mentioned, correct? I think that can be a short question answer. You're muted, Rob.
So part two is definitely yes, as I mentioned, in the Excel files, that it's just reading these tabs. So it's abstract enough for whichever data you're going to use. And then, as I mentioned, yes, any biomedical data. So it doesn't necessarily have to be radiological data, but if you have your own radiology distributions, you can load it right in, and you can directly compare it to the CDC or census, or if you have your own file that you want to compare representativeness to, or distribution you want to compare representativeness to. So it would technically have to be two different files to compare the representativeness between the two, but as long as each file has just the same, as I mentioned, just the same tab names and the same headings in your Excel, then it will be able to parse it.
Okay. So next question is, does this that's more for Heather, I think. Does Jensen-Shannon distance apply to one variable at a time, or can it be used for multiple variables at once?
I think there's two different ways to think of two variables at once. One of them we've already implemented. So in our JSD paper, which Emily has really helpfully linked to in the chat, we looked at the combination of race and ethnicity. And by combination, I mean for an individual, kind of how did they report those two attributes? And so that's one way of combining attributes, is kind of thinking for an individual, tallying two different things, and then moving forward from there. So we've implemented that, and anyone can go from there. The second one is kind of truly, joint distribution works. And so that's the question of saying, let's look at two different attributes separately and together. So that might be agent index and race, for example. How do we quantify representativeness of those, maybe kind of overlapping? And that's an area of ongoing research by MIDRC. So as you know, we have these collaborative research projects that were mentioned, and one of them is looking into the JSD, kind of to put it through its paces as a metric overall, to find out how it functions, or to not to find out, but to rather characterize how it functions in questions like that.
Okay, thanks. And a little more technical question for Rob. This is about the requirements. So an attendee is asking if other requirements would work too. So what if, for example, if you want a different version of NumPy or pandas or stuff like that?
Yes. So the requirements.txt, so at pip, it uses tildes. So that usually means that as long as there's a compatible version installed, it will allow it. So the requirements.txt does use that. you can try different versions, and I won't guarantee it, but I know I've on 3 different test machines, I'm using 3 different versions, but because of the tilde symbol, I know they're compatible and it's working.
Okay. All right. So a more general question for Heather, I think mostly. Could you please give us some guidance on how to interpret JSD? What is a good value? What is a bad value? Is 0.5 good or bad?
This is a great question. You know, how I see this in terms of the meaning of the JSD, it's in the context of the task for which you're trying to evaluate the representativeness. So someone might want to kind of maximize representativeness of the data that they're using for training and then testing to compare those. So they might be interested in having a very low, if not zero, JSD. Some people might be interested in taking an algorithm trained for one population and then testing it on another. And they're very much interested in, if these are very different populations, how does that work? And so they would be expecting to have a very high JSD, close to 1. So I think it really depends upon the task. And this is another area too, where we're trying to put the statistics through its paces and to kind of understand, especially, you know, as you go from 0 to 1, we expect a nonlinear relationship there because the JSD is the square root of the Jensen-Shannon divergence. So we're looking into that further through our CRP work.
All right, thank you. And then there's more of a comment, and I don't know if either one of you can comment on this, and the comment is, propensity score could be used to compute probability of a case being in one data set versus another given predictor variables. So average propensity score of MIDRC cases might be one summary measure of how representative it is of the other data set. So do you want to comment on that?
Yeah, I think this comment highlights about how many interesting and helpful tools and metrics there are from statistics. And then, you know, our work in MIDRC is to think about applicability to kind of this translation of AI questions. So we've looked at propensity score for a couple of different projects, certainly very interesting to us. But for representativeness, we're finding that JSD is kind of a nice metric, and we're continuing to work on that further. But certainly there's a lot out there in terms of statistics that are useful for these questions.
Okay, so next question is, how do you handle binning of data, like ages, for example, where you have different bin sizes, different granularity in different subsets, and what impact does that have? And what about missing data? How is that handled, for example?
Yeah, so that's actually an excellent point. So actually looking at our CDC age data, there's a lot smaller number of age ranges than we have in our MIDRC data. So that's actually handled through our config file. So I actually, in the config file, I'm setting up ages. And these are just the CDC ages because it has the smallest number of distributions. So when it parses the file, so there is there's a little bit of a description of this, but this is basically the tab name I'm looking at. So the Excel sheet name is age at index. So when it gets to age at index, it's using regex to read in the numbers and find out which categories are compatible. It will give a warning if it will throw something at you if the age, say I go to 35 and there's no 35 in here, it will say, hey, this file you're trying to open doesn't match what age ranges you're looking for. So there is a way to specify it, and that's how it's handling it right now. There is a setting in the config that you have to adjust for that.
Mm-hmm. And I'll add a couple of other questions that are coming through that comment. It's a really comprehensive comment. Thank you. You know, when we have patients that are over 89, as you know, we don't kind of, you know, actually track their actual age because it goes into de-identification questions. So those are just kind of going, you know, above 65. So for example, that's an example about how we work with that in terms of the age. We put them into the bin of over 65. You know, a separate question you're asking is kind of the size of the bin, and you're absolutely right. We have these research questions too. So for some of these categories, ordering is important. We've kind of been thinking about that. but for some of it's not. Bin size is more important. And so I'll comment in short, these are all areas of research for us in MIDRC to kind of think about this singular metric, how useful is it, and kind of what do we need to know about its nuances of its behavior. The last part of your question, which was about have we tried using AI to recover missing data from images? We have not looked into that. I think part of it's because that is a research question that someone could attempt, but for our purposes, we're working with the data as submitted by the submitters. So that's what we're working with in terms of MIDRC, but certainly, a research question that somebody else might be interested in for other purposes.
Okay, so I think the next question is about ChatGPT, and I think the question is if we can ask ChatGPT or another Gen AI platform to incorporate this. I think our answer right now is no, but as one of the testers of this tool, I can tell you it's super easy to download and just get it up and running. It's not rocket science. So this kind of ties into the next question. I see that a lot of data cleaning and structuring is needed before we upload to this tool. Is that right? So how about that, Rob?
I'll say I'll say two things first, and then Rob, I'll ask you to pipe in. On the question about ChatGPT and computation, I would urge caution. I don't know if you've ever tried to go to ChatGPT and ask it to calculate some things. It is not meant to compute. It can write code for you, for example, that you can maybe take and then edit from there. But I would caution anybody to be really careful about using ChatGPT to compute anything at this point. And then second of all, data cleaning and structuring, I think a positive way to think about that is it's just important to kind of keep things orderly for any research purposes. And certainly the design here of moving it into an open source tool depends upon a standardization. I think that's a really common thing to require. Rob, do you want to comment further?
Yeah, I would say, I did work in industry for a while, and I felt like, a big push even before, like for machine learning, like is good curation of the data is always necessary for whatever research you're doing. So, just better curation of the data and more accurate curation and setting that stuff up better can there's always the garbage in, garbage out. So the better your input, the better that's going to be. So I think that, yes, it's always going to be a thing, but I would say also, like Heather mentioned early in the talk, that's one of the goals of MIDRC is to be a place where people can access images, and a lot of this curation and setting up the data has already existed. So like I mentioned, the MIDRC file is something that was downloaded straight from off of from the MIDRC database. So and being able to directly use it. So if there's like data in MIDRC that isn't just chest x-rays, like we should be able to just download that and it will end up right in the format that we're looking for like this tool, for example.
Okay. We're kind of running out of time, but I have a very quick question, and that is like, if you look at a classification problem, for example, you tend to use like maybe ROC analysis and precision recall, or maybe other metrics. So there's always like adjunct metrics that provide different types of information. Are you going to look into other adjunct metrics to the JSD to make a more complete picture of the diversity?
Yeah, I think that's very much of interest to us, especially maybe, differences of categorizing or measuring representativeness, for example, of continuous data versus categorical. At this point, from our work, JSD seems to perform pretty consistently across all of them. We find it a very useful metric. But I think that's part of the excitement about the research projects in MIDRC is kind of always being open to learning and discovering and learning from other fields in our work too. So I absolutely agree with you that adjunct measures of representativeness are going to be really helpful, and we're going to continue to work on those, especially kind of curating those concepts specifically for AI of medical imaging.
All right. Okay. Let's thank both our speakers one more time, and also the attendees for their many questions. And we hopefully will see you all again in a month for our next MIDRC seminar in the month of June. So with that, I'd like to say goodbye and see you next time. Bye.